In the last video, we saw that if you wanted to take, I don't know, a plus b to the nth power, and if n is larger than really 2, but really especially larger than 3, it is very tedious to multiply it out, essentially using the distributive property, or kind of doing polynomial multiplication or FOIL, or however you learned it. It is extremely, extremely tedious. And then we learned the Binomial Theorem, which said this, that is equal to the sum from k is equal to 0 to n of n choose k, right? Where that was, what we learned in combinatorics as the binomial coefficient, and that's why it's called the binomial coefficient, because it's actually the coefficients in the binomial theorem of x to the n minus k. Oh, sorry, I keep writing x. Let me undo that. Edit, undo, edit, undo. Oh, it's taking too long. Oh, let me just. Oh no, that's not what I wanted to do. Let me erase it. Okay. Keep writing x. It could be an x, but then this would have to be an x here as well. Maybe I should do that. Of a to the n minus k times b to the k. So each term, the n stays constant, but each term you start at k equals 0 and you keep incrementing up. And we did an example to solve a plus b to the 4th power in the previous video, and as you saw, that was tedious, but less tedious than actually multiplying it out. And if you get really fast at computing, n choose k for different n's in k, it could be reasonably fast. So what I want to do is I'm going to show you a slightly faster method than what we just did, kind of a faster way to compute the binomial coefficients. And then after that, I'm going to show you a super fast way that, short of memorizing the coefficients, which I actually know some people who've done that, is a pretty amazing way to essentially multiply out any binomial. So what's my pseudo fast way of doing it? Well, I hinted in the last presentation that those coefficients were actually terms of a Pascal triangle. So what's a Pascal triangle? So if we start off with a 1, and then you just go. Actually, let me do it in the. Well, yeah, let me do it right here. And then, actually, let me start with 2 1s. And what you do is you take the sum of both of these. So that's a 2, and then you bring down a 1 to the left and the right hand side. And notice these are the coefficients of a plus b squared. Right? And these are the coefficients of a plus b. You could say a plus b to the 1, right? 1a plus 1b. This is a squared, 1a, so you could rewrite, a plus b squared is 1a squared plus 2ab plus 1b squared. So this is these are the coefficients of a plus b squared. Now let me arbitrarily switch colors. And so 1 plus 2 is 3. 2 plus 1 is 3. Bring down the 1. Bring down the 1. And now we have the coefficients for a plus b to the 3rd, which we computed in that was the very first thing we did. We actually multiplied it out, and we just know the pattern. The first coefficient is 1, so it's 1 a to the 3rd b to the 0, so we don't have to write the b, plus 3, we just decrement this exponent 1, 3a squared b plus 3ab squared, and then plus 1 a to the 0, which is just 1, b cubed. So that was pretty fast. And we could keep going down the Pascal triangle. So let's do the next one. So we can bring down a 1. 1 plus 3 is 4. 3 plus 3 is 6. And this is neat. That just very simply, you can actually generate binomial coefficients without having to compute them. Very simple, I guess you could call it an algorithm or drawing for 1. And it's symmetric, just as you would expect it, right? Because you could easily switch b and a. A plus b is the same thing as b plus a, so you should essentially get the same answer. And so we just, very quickly, we figured out the binomial coefficients for a plus b to the 4th, which was a lot faster than we did in the last example, right? A plus b to the 4th. So then I think you get the point, but so it's 1, let me write it in a different color. 1 a to the 4th, b to the 0, plus 4 a cubed b squared, b to the 1, plus 6a squared b squared, which makes sense that this is the middle number, and a and b have the same exponent at this point. And then plus 4a, we decrement it, b cubed, plus b to the 4th, 1b to the 4th, right? A to the 0, so that's why we didn't write there. So 1b to the 4th. Right? So once and that was very fast compared to what we had to do at the end of the last video, and then we could just keep going. For 5, so 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Bring down the 1. So these are the coefficients for the expansion of a plus b to the 5th power. And so this is a reasonably fast way of doing it, although it can get it'll take a lot of space, and it can work reasonably well, for up to a power of, I don't know, 8 or 9 or 10. Even then, it starts to get pretty big and cumbersome. But for powers up to 7 or 8 or 9, you could do this. You could draw it out really fast and do this, and it's probably faster than actually computing each of the binomial coefficients. Although you might be pretty fast at computing n choose k, in which you don't have to do this. So with that out of the way, let me show you an even faster way of doing it, short of memorizing it. And this will allow you to really calculate a plus b to the nth, to the 20th power, almost in your head, depending on how good you are at arithmetic in your head. So here is the trick, and I encourage you to experiment for why it works, but it does work. And I mean, and it's not even a trick. It's just, and this Pascal's triangle isn't even a trick. Pascal's triangle is just an alternative way to generate binomial coefficients. And what I'm about to show you is just another way of essentially generating the binomial coefficients, although it's probably a faster way to compute them. And it's a good project for you to think about why this works. So I'm just going to start with a very concrete example. Instead of a plus b, let me just do x plus y, just because you might see the binomial theorem written that way. So let's say x plus y to the 10th power. This would take me all day if I was to actually multiply it out. It would take me probably 20 or 30 minutes without making careless mistakes to actually figure out all the binomial coefficients. Maybe not that long, but it would take me a while. And to draw Pascal's triangle would fill up a whole page, and I'd still probably make a careless mistake. So how can I do this? So what you do is, so one thing that this is going to have 11 terms, right? Because you're going to start with x to the 10th, y to the 0, and you're going to go all the way to y to the 10th, right? So if you start at 0 and you go to 10, that's 11 terms. So this has 11 terms. What I want you to do is just write down just the numbers. You can almost count the terms. You don't have to go all the way to 11, and I'll show you. But let's write all the way to 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just squeezed it in. And you'll see you don't have to go all the way to 11. You could probably just stop at 6. So here's the trick. We know that the first term is going to be x to the 10th, right? We know that x to the 10th. And actually, we know that it's going to be x to the 10th. Then the second term is going to be x to the 9th. Then it's going to be x to the 8th. It's going to be x to the 7th. It's a little tedious. X to the 6th. X to the 5th. X to the 4th. X to the 3rd. X squared. X. And then there's going to be x to the 0, or just 1. Let me just do the y's. So this was x to the 10th. That's not bright enough, this color. So this is y to the 0, so we don't have to write it there. But then we have a y to the 1st, y squared, y to the 3rd, y to the 4th, y to the 5th, which makes sense. This is the middle term. Y to the 6th. Y to the 7th, y to the 8th, y to the 9th. And I don't want you to get confused. Each of these is a separate term. I don't want you to think I'm multiplying them all. Right? And then we just have to figure out the coefficients on each of these terms. Those are divider lines that I attempted to draw. I wasn't trying to confuse you more. I just wanted to, because they seem to be running together, each of the terms that I'm writing. but I think you know what I'm doing. So now we have to figure out the coefficients. And then this is the neat part. So we know that the coefficient on the first term, let me draw a dividing line here and here. The coefficient on the first term is always 1, right? So the coefficient's 1. So the coefficient on the second term is going to be the exponent on the first term times its coefficient, so 10 times 1, divided by the term that it is. So it's going to be 10 times 1 divided by 1. So it's going to be 10. The third term's coefficient is going to be the exponent on the x, right? So it's 9 times its coefficient, which is 10. So it's going to be 9 times 10 divided by the term it is. So it's going to be 9 times its coefficient, 10, divided by 2. So what's 9 times 10? That's 40. That's 90 divided by 2, which is 45. And you keep going. The fourth term is going to be the third term's exponent. So it's going to be 8 times, let me write this down in a different color. It's going to be 8, right? 8 times its coefficient times 45 divided by which term it is. So it's the third term divided by 3. Well, that's just 8 times 15. And let's see, that's 80 plus 40, so that's equal to 120. So that is the fourth term. And so then let me just draw these dividers. I know it's getting a little complicated. And I'm writing it all out like this, but if you practice this enough, you can actually just write it straight out. And so the fifth term, what is the fifth term? Well, you take the exponent on the x, so 7 times the fourth term's coefficient times 120 divided by 4, right? Divided by the previous term by 4. Well, that's just 7 times 30, which equals 210. That's the fifth coefficient. What's the sixth coefficient? Well, it's 6. It's 6 times, so the exponent on the x times 210 times its coefficient times the fifth term's coefficient divided by 5 for the fifth term. Well, 5 goes into 210 how many times? 42 times, right? So it's 6 times 42. That's 240 plus 12. That's 252. Right? 252. And then once you're at the middle point, right? The sixth term is the middle term. You'll see that you start going back the other way. And we learned one from the Pascal's triangle, or even the definition of the binomial theorem, that the coefficients are symmetric. So we know that the next one is going to be the same. This was the middle one, right? So we know the next one's going to be 210. It's going to be 210. And you could calculate it using the same system. This is just a quick way of doing it. This one's going to be 120. This one's going to be 45, and this one is going to be the 10th coefficient. This is going to be 10, and then of course the last coefficient is just 1 y to the 10th power. So if I were to write this out, the answer is, and if you practice this, you'll find that you can do it quite fast. It's x to the 10th. X to the 10th plus 10x to the 9th y plus 45 x to the 8th y squared plus 120 x to the 7th y to the 3rd plus 210 x to the 6th y to the 4th plus 252, we're already at the middle term, x to the 5th, y to the 5th, plus 210, x to the 4th, y to the 6th. I'm running out of space, but you can hopefully extrapolate what I'm doing, and it makes sense to you. And hopefully you have an appreciation that if you actually had to multiply out x plus y to the 10th, it would have taken you all day. Maybe I'll do one more video with a smaller example to show you that it's a little less complicated when you do, say, x plus y to the 6th power. See you soon.